Welcome to another short video segment in which I'm going to describe what happens when we put multiple capacitors together with each other in an electrical circuit. In this particular segment, you're going to be seeing some circuit symbols for the first time. And these are things we'll be dealing with more directly in the lab. I also want to show you here what an actual capacitor might look like. There's lots of different forms, all of which have one thing in common, and that's that there's two little wire leads coming out of them. So whether they look like a little barrel or something flat. And then the diagram down in the lower left shows why they can make two flat parallel plates of metal look like a barrel. And that's because it's all rolled up nice and tight with a little dielectric paper separating the two sheets of foil, and each of the pieces of foil is ultimately attached to a little wire lead that pops out of the top or the side of the capacitor. So it's kind of interesting to look at the anatomy of one of those things. So what we're going to do here is use the QVC relationship that I've shown at the top, along with the relationship for parallel plate capacitors capacitance, to show what happens when you put multiple capacitors together in a circuit. So down in the lower right, you see a typical capacitor circuit where we've put a battery, and that's got the symbol here like that. Got a positive and negative terminal, and it's connected via some wires. The wires go along here. We draw them very square-like, but they're not always square. Wires can run any which way. It's just easier to draw if they're square. And then those wires terminate on the leads of the capacitor. So we see the plates there, and this shows the capacitor already charged up. So if we had numbers, we could figure out just how much Q will go on that capacitor for a given potential difference across our battery. But what happens if we take another capacitor, and just to keep it simple, we're going to use one that's identical to the first, and we connect them so that the two sets of plates touch each other, something like that. I hope you can see that an important characteristic about that capacitor is now different, and that is the area. We've just doubled the area of those plates by bringing two identical ones in contact. And we haven't separated them by any greater distance, and of course epsilon sub naught is no different. So the effect of this is that we have proportionally increased the capacitance of that arrangement. You could also describe it using the first relationship, that those metal plates are still in contact with each other. So if I shade in here in red all of the places in this circuit that are at a higher potential, that would include the wire, the positive terminal of the battery, and the entire left side here, everything made of metal. And then I'll shade in blue everything at a lower potential, and that's all of these wires over here, plus the blue plates over here on the right, and the negative terminal of the battery. So we still have the same potential difference across it. So if we have increased the Q, doubling it, that's another way to see why we've increased the capacitance of this capacitor. We've just given it the ability to hold more charge. So adding a second one will double the capacitance, and you can imagine if we bring a third one over here, we could triple the capacitance that way. So in general, and this works for non-identical capacitors as well, if we arrange capacitors in this arrangement, and this is known as being in parallel, with the positive plates attached to each other and the negative plates attached to each other, we say the equivalent capacitance of the whole arrangement is just the sum of all the individual capacitances of the capacitors that make it up. And we could do just as many as we want. So the equivalent capacitance, if you want to think of it this way, it's like if I were to just take this whole arrangement here and put one wire coming out of it, rather than, looks like three individual leads on each side. Just one wire on each side. They are now connected in parallel, and they have a capacitance that is the sum of all the individual capacitances making it up. So that was a parallel arrangement of capacitors, and I'm going to show you another way to connect capacitors to each other, known as the series arrangement. Now this takes a little bit more manipulation on my part on the diagram here, but this I might describe as like putting the capacitors end to end with each other. So if we just ignore for a moment that these capacitors have charge on them, I'm going to show you how that's going to be different in just a second. So if we connect these two ends to each other, I'm going to have to change some wires around a little bit here. So let me get rid of some of this wire that's already here first. So you see now I've done a little rearranging. I moved some wires so that I could squeeze this other one in. Now let me show you what effect we have here. So we still have the same battery that we had before. But what's different here is I can't have that same potential difference across both of these capacitors. Because, for example, if I had, let's say, a 9-volt battery here, there's no way I could have a 9-volt drop this way and yet another 9 volts across here, because that would be a total jump of 9 but a drop of 18. And there's something known as Kirchhoff's loop rule that was described in section 4 that says if you're going around a circuit like this, by the time you get back to where you started, you have to have the same amount of drop as what you had in a jump. And so what this tells us is that if these are identical capacitors, they're each only dropping 4.5 volts across here. Notice I'm going from the high to the low side. So that's why it's a drop. So those two together show how I lose all the potential that the battery is increasing. Well, with these capacitors, if I only have half the potential difference across them as what I would have at 9 volts, then I must also have only half the charge. So let's see what must happen here. I can't have what they've drawn here as 4 charges. I must only have 2 charges. So I'm getting rid of half of them. And this is just an example. Of course, these aren't real charges, just showing that we have half as much charge. And so let's think for a moment about what the battery had to do. It had to move half as much charge through its 9 volts as when there was only 1 attached to it. And if we look at the relationship up here, the battery moving half as much charge means it seems like that arrangement of capacitors has only half the capacitance as what a single capacitor did. Another way to think about this, using that equation on the right up there, is if we look at the center section here that I'll circle, this whole part is one piece of metal. We got 2 plates, we got a little wire in between them. So one piece of metal can be replaced by another piece of metal of any shape at all. So if we just put something like that in there, I can get rid of this stuff. So we have, in effect, made a capacitor that is wider or further in distance from one end to the other end. And in fact, in this case, we have doubled that distance. So think of that as increasing the distance separating the positive and negative plates. And increasing the distance has a proportional decrease in the capacitance of a parallel plate capacitor. So either way you look at it, from the equation on the left or the right, we see a decrease in the capacitance when we put these capacitors in series with each other. Now in this example, just for simplicity, I've used identical capacitors, but more generally, if we put any capacitors in series with each other, they have an equivalent capacitance found this way. I call it adding as inverses. So you take the inverse of each capacitance that you have, and I did 2, but I'll show that we could do 3 or even more. Take the inverse of those, add all the inverses, and then invert that sum when you're done. Sometimes this is written in fractional form, and it might remind you of something that you've seen before when we studied springs in series and parallel, and that's very, very true. So that's a nice generic way to describe the total effect of putting these capacitors in series. This has the effect of reducing the capacitance, where the parallel arrangement always has the effect of increasing the capacitance. So if I go to Radio Shack and I buy some capacitors, but I find that they don't have the size that I want, I have infinite number of ways to connect these together in series and parallel, and I'll show you in a next video combinations of series and parallel so that I could get as many different capacitance values as what my circuit might require. I think I'm going to leave the rest for another segment and leave it at that.